Hi, my name is Zach Thomas, and this is my Experiment 3, a macroscopic view of DC and RC circuits. The purpose of this experiment was to predict the behaviors of circuits containing resistors in series and parallel, and to measure conventional current. PhET online software was used to produce the circuits and test the different situations. Another purpose was to measure the potential differences across different resistors and to calculate an experimental RC value that will be compared to the hypothetical RC value. As you can see in the results, the hypothetical RC value was found to be 6, which matches the calculated RC value of 6.02. Some physics principles used included the conservation of energy, conservation of current, Ohm's law, and time constant, which is shown on the right. So for the series circuit, I found that I1 equals I2, and they both equal 0.02 amps. As you can see on the right, you can see I1 and I2 with the 2 ammeters. I also found that the current does not change after reversing the ammeter, but I becomes 0 amps with the voltmeter instead of an ammeter because the circuit becomes an open circuit. So what this means is basically when you swap a voltmeter for an ammeter, I becomes 0 amps. The initial conditions for this experiment was the circuit shown on the right, and the system is the circuit and the surroundings are everything else. So here are the potential differences across the different checkpoints. It starts at 3 volts but decreases from C to D and from E to F until it reaches 0. The sum is -3 volts and round trip is 0 volts. So on the right is a diagram for the circuit going through the different checkpoints from A to B, B to C, C to D, D to E, E to F, F to G, and G to H, and then H to A. And here is a graph showing the voltage from these different checkpoints. So as you can see, it decreases from C to D and also from E to F. And it becomes 0 from E to F and then F onwards. Some observations I found were that because the voltmeter has a high resistance, no current can flow through it, so the current in the ammeter does not change. When the ammeter is placed parallel to the current changes to about 0.06 amps. I found that the R47 resistor has a resistance of 48 ohms and the R100 resistor has a resistance of 102 ohms. Some possible errors include miscalculations, errors with the PhET software, as well as human error. So here are 2 questions for the RC circuit. The first is, connect the batteries to the 10 ohm bulb and capacitor in series. Observe the light produced by the 10 ohm bulb. What happens to the light? I said that the light bulb starts off brightly lit but then dims as the capacitor charges. The next question is, when you first connected the battery to the capacitor and the 10 ohm bulb, the capacitor was charging. What happens to the current in the circuit? When you remove the battery from the circuit, the capacitor begins discharging. What happened to the current in the circuit? I said that the current in the circuit decreases until it reaches 0. So here's the data for the experiment. I found the experimental RC to be 6.02, and this was found by doing -1 divided by the slope of the ln of the voltage difference divided by the initial voltage difference at time 0. This ended up being -1 divided by -0.1661, which is 6.02. And the -0.1661 is the slope of the ln, which you can see in the top right. And this is very close to the hypothetical RC, which is 6. The equation for the line is on the right, and the formula to find the experimental RC is shown below that. So here are the 2 conclusion questions. The first is, what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about the real ammeter and how would it have affected the circuits you hooked it up to? My answer to this is that an actual ammeter would have a resistance, so this would affect the current in the circuit. The next question is, what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? Explain. My answer to this is the ideal model predicted that the capacitor would reach full charge instantly, but in real life, the capacitor would take longer because of wire resistivity.